Hey everybody, it's Dr. D. Welcome back to our the last of our hypothesis testing introductory videos. Today what we're talking about is the final step, hypothesis testing step 5, where we're going to compute a p-value and we're going to draw a conclusion. We're focusing on tests of mu(x), the population mean when we know sigma, and we'll look at other tests in the future. But for now, I just want to draw attention. We've gone through the other 4 steps. We've formulated hypotheses. We've chosen a level of significance. We've chosen a test statistic, and at this point, we assume that we've calculated the value of the test statistic. Now, what we need to do is we need to choose a p-value and a conclusion. Oops. So let's look at step 5, the p-value. Choose a p-value or calculate a p-value, or compute, whatever you want. Compute a p-value and draw a conclusion. So in step 2, we chose a level of significance, and we defined that as how unlikely a sample would have to be, assuming the null is true, for us to abandon our belief in the null. Our p-value, and I've said this before, I'll say it again, every number is the answer to a question, right? This p-value is the answer to this question: how likely are we to observe a sample like this, like the one we actually see, meaning with our test statistic, if H0 is true. So under the assumption that the null is correct, how likely are we to observe a sample like the one we happen to see? And the answer is, well, it's going to depend on what the hypotheses are. So we're going to look at some scenarios. We're going to have a left tail test that we'll look at. We're going to have a two-tail test, and we're going to have right tail tests. And if you want to learn more about those, go look back at step 1. And in each of these scenarios, we're going to consider possibilities. So this will cover all possible cases. I'm just drawing some quick results here. It's possible that we would get a z value that is less than 0, meaning a negative z, right? So after we finish step 4, we could get a negative z value. Or we could, and that's why I'm going to add 3 more here, we could get a positive z value, right? So that would depend on whether our sample, if you have your z-score formula, you'll know that you got z equals x bar minus mu 0 over sigma x bar. If your x bar is greater than the hypothetical mean, you'll end up with a positive z. If your sample is less than the hypothetical mean, you'll end up with a negative z. So those are the 2 possibilities. So let's look first at left tail z-score less than 0. That means it's going to be over here on the left, right? You're going to have some z, say it's right here. That's the z you've calculated. Well, for all left tail tests, your p-value is the area to the left. And so in this case, this area right here would be your p-value. And you would have to calculate this. How would we calculate this? Well, once you have your test stat, norm.s.dist gives you the area to the left, right? Z1. And so if you've got a left tail test, it's pretty straightforward, just norm.s.dist Z1. Now, if you have a left tail test and your z is greater than 0, your z goes over here. And then you can see that your p-value, right, is going to be this area. It's going to be greater than 0.5, right, because it contains the entire left half and then some. But you calculate it in exactly the same way, norm.s.dist. If you have a right tail test, let's say you have a right tail test, and you have a negative z, well, your z is over here. That's your z. Negative 1, negative 5, negative 1.5, well, who knows. Then this area right here, since it's a right tail test, your right tail is your p-value, which means this area here is going to be your p-value. And again, you can see that's going to be greater than 0.5 because it contains the whole right half. And then similarly, if you have a right tail test, but you've got a positive z, and your z is over here, then your p-value is going to be the tail. And that's going to be less than 0.5. In this case, norm.s.dist gives you the left tail, right? That's what it kicks out. And so this is going to be 1 minus norm.s.dist of your z value, comma 1. And that's how you would calculate the right tail. For the two-tail test, It's a little bit trickier. It's not quite as obvious what you're going to do. But it's useful to know that the two-tailed test is measuring how far away from the mean you are in absolute value. It doesn't matter what we want to know. It doesn't matter if it's positive or negative. We just want to know, are you far from the mean? And if you're far from the mean, then we want to reject the null. So if you have a negative z, what you're going to do is you're going to find this area over here, the nearest tail, and this area that's right here times 2 is going to be your p-value. And if you have a positive z, then you're over here. Again, we don't want to know about this. We want to know how far away you are. So it's going to be this area times 2. That's going to be your p-value. Because essentially what you're testing is not just that area, but also the equivalent area on the other side, right? So instead of adding these two values together, you can just double the area you have because you just want to know what's the chance that you would end up that far or farther away. Now this is a little trickier because in this case, this is going to be 2 times norm.s.dist of z comma 1. And this one is going to be 2 times 1 minus norm.s.dist, which drives home the point I've been trying to make for a long time, which is draw the picture. Right, the pictures are really helpful. They prevent you from making mistakes that you shouldn't be making, and drawing the picture really does help you build the intuition. Remember, the goal in this class, the goal in this work is not to get the right answer. It is to learn. You will eventually get the right answer if you learn, and you'll get the right answer to harder problems if you learn. But taking the shortcut here is just going to shoot you in the foot later. So you want to make sure that you're really bringing your whole self to these questions, trying hard, grappling with difficulty. Okay, once we have our p-value, once we have answered this question, how likely are we to observe a sample like this? That's computing the p-value, if the h0 is true. The next thing we have to do is draw a conclusion. To do that, one of the really nice things about the p-value is it gives us a straightforward approach to this. We are going to have a rejection rule. This helps us know, and everybody knows why we rejected the null if we did. This says that if our p-value, which is how likely we are to observe a sample, is less than alpha, which is how unlikely we said we would have to be for us to get rid of our null, then we are going to reject h0. And because we chose h0 and ha very carefully, they're exhaustive and mutually exclusive. When we reject h0, we are going to accept the alternative. We have rejected the null. We have accepted the alternative. And that is the example I gave back on the intuition video of an inconsistency. This is an inconsistency. We said that there was a certain benchmark likelihood we would have to meet, and in fact, we saw a sample that was more unlikely than that. And that means we reject the null. There's the inconsistency. So we're going to side with our observation. If, on the other hand, we have a p-value that is larger than alpha, then we are going to fail to reject the null. And those are the two options. You can reject the null, or you can fail to reject the null. This is a way of saying this is that our test was inconclusive. Right? We failed to reject the null. The test is not designed to accept the null. We assumed it was true. It would be circular reasoning to go through a process that then led us to conclude it's true. So we can reject or fail to reject the null. If we fail to reject the null, we simply leave alternative out of the argument. But that's what it comes to, right? So we have chosen a p-value, or we've chosen a set of hypotheses. We come to a p-value. We compare that p-value to alpha, and then as a result of that, we either reject or fail to reject the null. What about if p is equal exactly to alpha? Well, that should never happen, right? You just need more decimal places. Eventually, if you just go enough decimal places, the chances of getting the sample you got is never going to be exactly 0.05, right? And so we don't need to worry about that. The probability of that happening is actually 0. And so we're either going to end up with a p-value that is a p-value, right? Our p-value is going to be less than alpha, or our p-value is going to be greater than alpha. Now, how do you remember this? I don't know, write it down, study a lot, practice. One of my classes came up with the mnemonic device: reject small values of p RSVP. So I don't know if that's useful for you. But if your p-value is small, what that says is the chance of seeing a sample like this, if the null is true, is really small. Maybe the null's not true, right? That's what we're really trying to get at here. Okay, so that's the last step. Step 5 is to compute a p-value and to draw a conclusion. And with that, we have now learned all the steps that we need. I think it's very difficult to put these into your brain without practice. And so the next video is going to be just a practice problem. We're just going to work our way through it. I'm going to walk through these 5 steps again as we go to really try to drive it home so that everybody can walk away feeling like, okay, I've seen this done once before. And then after that, once we've practiced a little bit, we're going to see what happens when we get rid of this this last terrible assumption. We reintroduce this terrible assumption, and I didn't really draw attention to it, but we're going to look at what happens when we don't know sigma. We have to deal with S. I hope you found that helpful. Learning how to calculate a p-value using Excel is important and useful, and then learning how to draw a conclusion will come in handy. Next time, I look forward to seeing you and putting this into practice. I'm Dr. D. If you have questions, that makes total sense. Please comment. Please send me an email. I'm happy to interact with you. And I will see you all next time. Bye.